Welcome back, everybody. We're going to start
Everyone,
session 3 of our conference. Please be seated. The theme for this session is sustainable energy and energy storage. Sustainable energy systems are novel anthropogenic innovations conceived with the primary goal of providing clean, reasonable, and accessible energy with a benign environmental impact. The need to preserve the environment while parallelly powering the present and future is of utmost precedence today, which sustainable energy systems and storage mechanisms can achieve. From a broader perspective, science, technology, and innovation in this domain through mega projects within SCO member states can directly benefit from the economic standpoint. Alternatively, sharing knowledge at the SEO common platform can ignite the SEO young minds to find a way out to materialize and operate sustainable energy systems and storage possibilities, employing local process inputs and human resources rooted towards the judicious vocal for local notion. As before, there is a question and answer session at the end of all the talks where we'll be taking questions from both online and offline participants. This session will be chaired by Dr. B.L.V. Prasad and Dr. Ramakrishna Matte. Dr. Bhagavadullah L.V. Prasad is the director of the Center for Nano and Soft Matter Sciences, CENS, Bangalore, and a senior principal scientist at the Physical Materials Chemistry Division of National Chemical Laboratory, CSIR NCL, Pune, India. Dr. H.S.S. Ramakrishna Matte is a scientist at Center for Nano and Soft Matter Sciences, CENS, Bangalore, India. We welcome both the chairs to this session. The first speaker of this session is Nikhil Kumar, who is a scientist at CSIR National Metallurgical Laboratory, NML, India. His talk is titled as Development of Efficient Triple Conducting Electrode for Protonic Ceramic Electrolysis Fuel Cells.
and a very good morning to all. This is Dr. Nikhil from CSIR NML Jamshedpur, India, and I am going to elaborate my research work in this SCO Young Scientist Conclave. And the title of my research work is Development of Efficient Triple Conducting Electrode for Proton Ceramic Electrolysis or Fuel Cells. In this way, we can, as we all know, that the fuel cell is a technology by which we can convert this chemical energy of hydrogen or other fuels to efficiently produce electricity. Or electrolysis cell is a reverse process of a fuel cell where we split water into hydrogen and oxygen. So in this figure, we can see that in the fuel side, this is hydrogen that is converted into protons, and the oxygen side, this proton is mixed with oxygen, and the byproduct is water. So here we can see that this is the fuel cell, and in the right side this is electrolysis cell, which is reverse of this fuel cell. In the fuel side we have used this S positives to make hydrogen, that is HER, hydrogen evolution reaction, and the oxygen side it produce oxygen, so it is oxygen evolution reaction. So the main feature for this kind of cells to select the material is the material should be triple conducting materials. It means it should conduct as positive protons, oxides, or electrons, as well as it should have sufficient active sites and have a superior contact of phases between two boundaries of phase. So there are so many advantages of this proton ceramic fuel cell applications that they have a potential or efficient upgradation of solid oxide fuel cell. They are extensively used for off-grid power and vehicles, and they can used in reversible operation to store renewable energies, as well as a very good feature is they can operate at intermediate temperature, and the quality of non-fuel dilution at anode during operation. And the use of the main thing is that we can use different kind of fuels like hydrocarbons and ammonia in this proton ceramic fuel cell. And and now the US or the world is looking for this kind of technology. So this is the just global market of North America for the proton ceramic fuel cell. So we can see the market was $46.5 million in 2021, which has increased in 58.7 million for 2022, and now they are expecting to grow it 396.6 million by 2029. In this way, we have used these perovskite materials for butter splitting reactions and fuel cell applications. So perovskite, as we all know, these are the common metal oxides which have a general formula AVO3. And when we extend these perovskite structures to make double perovskites, so it's just it is a single layer. Then this is alternate layers of different A side and B side metal ions. And the main characteristics of this type of metal oxides, perovskites, are they have a compositional flexibility. We can substitute A side as well as B side or anionic side by different kind of metal ions, and they have very good electronic properties as well as they are environmental friendly. It means they are very much unreacted from the gaseous environment, as well as they are very stable at high temperature, and they have a very broad application field. And they can use it for butter splitting, solar cells, LED applications, optoelectronics, or X-ray detectors. And we have used this solid state reaction to synthesize these perovskite materials. So here, for example, in our lab, we have developed this material, calcium lanthanum scandium ruthenium OC, which is a double perovskite where calcium and lanthanum at A site and scandium ruthenium at B sites. So here we have used carbonate and basic metal oxides and grind it for 1 to 2 hours, and then kept it at high temperature for 15 hours, and again intermediate regrinding, and again kept it for 300 degree for 24 hours, and we got this CLSR pure phase materials. Like this, we have made a series of this kind of material, just the substitution at A site by strontium in place of lanthanum, and another material by substitute iron at place of scandium. And we have published all these kind of materials for butter splitting reactions. After synthesis of these materials, we have collected these XRD and neutron powder reflection data, refined those data, and we found that this is a pure single phase. And this is Ritwell refinement data, and we can see clearly that all the peaks having their Bragg's peaks, and all the parameters are in a very good range. And all the characterizations, and we use these materials for butter splitting reactions. Here we can see this is oxygen evolution reaction, where these oxides are converted into oxygen by using 4 electron pathway. And in the second side, this is oxygen reduction reaction, which is a half cell reaction for fuel cell applications. So for that CLSR material, when we compare our data from already reported material, then we found that it is a very good onset potential for ORR activity, 0.9 volt, and which is very equivalent to the benchmark catalyst with benchmark platinum carbon, and a very good data for onset material for OER catalyst. And this benchmark is RuO2, but still the stability of our material is high as compared to this RuO2. These kind of water splitting reactions we are trying to fabricate a whole cell with EC as well as FC applications. So we use these kind of perovskite materials to make the electrodes, or cathode for fuel cell, or anode for electrolysis cell. So there are two types of cells: anode supported, where we are using this electrolyte at anode. The anode is made up of anode plus electrolyte, and the electrolyte is a solid dense porous materials, this barium, cerium, yttrium oxide. So this the images of anode plus electrolyte. The one side is anode, and then we have deposited this electrolyte. Then we have used our material OER paste of that plasmodium nickel oxide material over here by screen printing or by hand printing. So this is the whole cell, which we can use it for now test. And we use this cell for SOFC testing as well as PCC testing. So we found that this is very good for SOFC testing, but when we use the same cell for PCC, then we have realized that the OCV is little bit low, as we were expecting it at least 1 volt, but it is almost 0.8 volt. So we need to fabricate the cell in a different manner. Tried to change the electrolyte, then we have substituted zirconium as well as yttrium in the electrolyte section, and we have followed the same procedure, and we used this new cell for this testing, and we found that now we got OCV value was fine. It was approximately 1 volt, but the IV characteristic results and EIS curve was not very good. It's not up to the mark. So this is the very basic data for is a Nyquist plot, and IV for that same is the data for IV testing for ECFC mode and EC mode. Then this is the metal supported cell where we used vanadium metal as a anode in place of nickel oxide, and anode supported cell where we used nickel oxide and electrolyte. So here only we use vanadium at anode, and then this barium sodium deuterium oxide is electrolyte, and this OER same paste is cathode. In this picture we can clearly see that this is vanadium surface which is anode, and this is sputtered electrolyte which is our electrolyte BCYO, and this is OER paste which used here as a cathode. This is the whole cell. We have tested this, and although our results were not good as we were expecting, so we have tried different strategies by using the same kind of strategy for metal supported cell. This is a very new area, so people are interested in this field, and there are a lot of opportunity to extend this PCC and FC fuel cell application area. So I would like to collaborate my work, and I welcome all the collaborators who are interested in my work from India as well as different SEO countries, and I would like to extend this work for up to for a good level. So who are interested, please come to collaborate. And at last, I would like to acknowledge our director CSIR NML Jamshedpur and head of our MP division, member of functional group materials, and lab mates and research colleagues as well as non-teaching. Thank you very much for your kind patience.
Thank you, Nikhil. Our next speaker is Ivanova Nataliya. If you could raise your hand. She's the lab head of the National Research Center from Russia. Her talk is titled as New Type of Electrodes for Electrochemical Devices with Proton Exchange Membrane.
Hey dear colleague, I am going to present my report at this event and thank you for this opportunity. The title of my work is New Type of Electrodes for Electrochemical Devices with Proton Exchange Membrane. The global energy storage and serious environmental change due to the high burden of the fossil fuel usage. Additionally, their consumption cause the climate change and air pollution due to the greenhouse gases and other byproduct generation. The development of distributed network of low power generation makes the development of hydrogen energy promising, particularly fuel cell with polymer electrolyte membrane, fuel cells, as electrochemical current sources. Hydrogen technology are rapidly developing in the world. Proton exchange membrane fuel cell are one of the most promising hydrogen electrochemical systems. Fuel cells have a number of important advantages: fast startup, small size per unit of generated power, and low operating temperatures. Modern hydrogen-oxygen polymer electrolyte membrane fuel cell contain a thin central proton conducting polymer membrane with a plasma-containing catalytic layer on each side. The whole is sandwiched between two carbon-based gas diffusion electrodes, generally made up of a gas diffusion layer and a thin microporous diffusion layer in direct contact with the catalytic layers. This slide presents the steps of membrane electrode assembly preparing. Fuel cell performance is significantly determined by commonly used carbon-supported platinum-based nanostructured electrocatalyst. The dissolution of platinum, the particles enlargement, and the carbon-supposed corrosion are the main reason causing a loss of activity and a decrease of the catalytic electrochemical active surface area. A decrease in the platinum content and an increase in the activity and durability of electrocatalysts are important for the commercialization and widespread introduction of fuel cells. The variety of shapes and structures of carbon supports allows for creating efficient electrocatalysts. Nowadays, there is a wide variety of carbon nanomaterials. Nanofibers, various configuration of tubes, fullerenes and carbon black, reduced graphene oxide and carbon nanotubes. As you can see, carbon nanotubes are two-dimensional nanostructures formed by a rolled sheet of carbon. They can be single-walled and multi-walled, as well as form arrays. The electrochemical performance of the catalytic layers is determined both by their chemical deposition, type and content of platinum, and by their microstructure. This catalytic layer can be manufactured using a variety of methods. The use of nanotubes as a support using standard synthesis method, polyol reduction method, forms the catalytic layer shown on the slide. You can see the mass structure of it. The dispersion of catalysts and the method of the application leads to the destruction of the structure of the tubes and the low efficiency of the catalytic layer based on them. In this regard, it's interesting to form a new type of electrodes. The electrodes as a complicated system consisting of gas distribution layer, microporous layer, and catalytic layer. Using complex carbon structure, nanotubes, as you can see on the figure. The first step is CNT array growth on carbon paper cloth. Magnetron sputtering is in the mode of direct current used to create a compact nanostructured nickel film with the average particle size of 3 nanometers. The obtained compact, highly uniform distribution film with a low specific surface and a narrow nickel agglomerate size distribution has been successfully used as a catalyst for the growth of CNT array in the process of pyrolytic gas phase deposition directly onto the gas diffusion layers. The diameters of the obtained nanotubes are 40-60 nanometers. The step is forming the enough thickness of the SNT array for using as microporous layer. As can be seen in figure, the growth of the SNT array leads to an increase in the diameter of the carbon fibers of the initial gas diffusion layer, the change in which can be used to calculate this thickness. Since the array of SNT is both a support of catalytic particles and acts as microporous layer, its thickness should be sufficient. For one stage, the obtained thickness is not enough. However, using methods of layer-by-layer deposition achieves the required thickness of the SNT layer. This process is shown on the figure. The third step is the catalytic layer based on CNT array. To estimate the effect of geometric parameters of a CNT-based support, a semi-empirical model was proposed using a random uniform distribution of particles over the CNT surface. An increase in surface area with decreased platinum loading of the catalytic layers was shown for the CNT-based electrocatalyst. Based on the obtained distribution, the surface area of the electrocatalyst was estimated and further used to evaluate the performance of the catalytic layer as the part of fuel cell. Step is preparing the catalytic layer based on CNT array. The microporous layer was first impregnated with the platinum precursor salt by soaking in aqueous solution of the salt. Then the salt was reduced in the form of platinum metallic nanoparticles in neutral using hydrogen gas medium. The resultant structure is shown on the slide. And this slide presents the investigation of the electrode preparation by using impregnation reducing methods. The durability of these electrodes is approximately 2 times higher than the durability of the reference electrode. A possible explanation for such situation is provided by XRD date. The improvement may be caused by the incomparison of heteroatoms, mainly carbon, in the crystal lattice of platinum particles, leading to stronger mechanical and electronic interaction between platinum particles and surface carbon atoms of the microburst layer. A method for manufacturing electrodes of new type has been developed in this research. I want to present you my team. We are always ready to cooperate.
Thank you, Nataliya. Our next speaker is Praveen Kumar, who is an assistant professor from the Indian Association for the Cultivation of Science, Kolkata, India. The talk is titled as Spin Manipulation and Basal Plane Activation of 2D Materials for Photoelectrochemical Hydrogen Generation.
Hello everyone. First, let me thank the organizer for giving me a chance to present the work which we are doing at IICS Kolkata. I'm Dr. Praveen Kumar, and today I'm going to discuss spin manipulation and basal plane activation of 2D material for photoelectrochemical hydrogen generation. So before I go into the technical part, let me tell you a brief about the work which we are doing at IICS Kolkata. So we work on semiconductor nanostructure, especially for nitride, oxides and silicon. Then we try to understand the various fundamental issues on 2D material, especially for chalcogenide and MXCs. And we are also working on quasi 2D material. And once you have these very wide range of material, then we try to understand their heterostructure, and especially we try to understand their electron transport as far as their momentum and spin is concerned. And once you make the heterostructures, you can change the various properties, and you can make devices like a broadband and cell power photodetector. And we are trying to address the energy density issue in supercapacitor. We are also working very rigorously on photoelectrochemical and electrochemical water splitting and CO2 reduction. And just to understand more in deep the mechanism behind the electron transport and with the momentum and spin, we try to understand them using DFT. So this is what we do at IICS, and what I am going to talk today is the work, a part of the work which we do for the photoelectrochemical water splitting. And especially if I talk about the photoelectrochemical water splitting, like it has a anode and cathode, and whatever anode is active to the light, it is photoanode or photocathode. So basic idea is just to have this material innovative, so that you can excite this electron and hole, you can separate and also do transport. So this is how you have to do it. You need a material where you can have a highly efficient separation and also highly efficient transport. So a lot of materials has been reported, starting from the TiO2 to nitride, and we are also working in several materials. But I'll discuss today related to the 2D material, which are the work which we are doing. So if I tell you about the 2D materials, there are more than 140 2D materials, but there are a lot of issues as far as fundamental is concerned. Some of the issues which we can address, like facile and affordable synthesis of these 2D materials, and electronic conductivity, because if I see here, this chalcogenide has a very low mobility. So that is where when you mix it with this MXCs, we could able to address this electronic conductivity. We are also worked on the critical bend alignment, and also the new topic which we have started at IICS, the spin or use the spin of the electron, which has been ignored till now. So as far as the facile synthesis is concerned, we have recently developed two processes at the room temperature chemical processes, by which you can get this 2D material in a layered exfoliation high quality, and you can see the comparison between the industrially available and the method which we have made it. So we have filed the 2 patents, and we have also addressed a very recent issue related to the heterostructures. So to get the efficient charge transport, we have heterostructures most to be the gallium nitride to get a very efficient photocathode. But what I am going to discuss today in detail, how we can activate the basal plane of MOS2, and how we can utilize the spin in Janus 2D material. So coming to the first part, if I say that MOS2 has been theoretically predicted as alternative of platinum, but because of the less active of the basal plane, only the edge side and corner side of MOS2 is active, the efficiency of that particular material is not as predicted by theoretically. So people are trying to modify it by platinum, palladium, but that is not the solution overall when you are talking about the commercial scale. So then the defect engineering comes into the picture. But once you do the defect engineering, it is very harmful for the recombination in the PEC. So that is not the solution for PEC. And the other solution has been projected by using the 1T phase, which is metallic phase. So once you use the 1T phase, then it becomes metallic, and it's also not a solution for photoelectrochemistry. Heterostructuring can be solution, but it is mostly reported in theory. So if I summarize, the more or less the work has been reported for only the valence band electrochemistry, but once you excite this electron to the conduction band, there is no report how to activate the basal plane. So we have walked into that. So what we have done, we have made the heterostructures using the MOS2 and MOSE2. So in one experiment we have taken MOS2 on top, in other experiment we have taken MOSE2 on top. So this first we have addressed the material science issue, so we have characterized them. So we have taken the silicon to silicon nanowire just to increase the surface area, active area, and after characterization we could able to confirm the growth not only by morphology but also from the structural and optical properties. And this you can see the complete device where you can see the silicon phonon, MOS2 and MOSE2. So after confirmation of the phonon, then we try to understand their electron transport, and when you understand this valence band and core level spectroscopy from XPS, it says that red shift in selenium and blue shift in this sulfur, and it tells you that the electron transfer is happening from MOSE2 to MOS2, and that same has been later proved by the valence band spectroscopy. And we have also done the mode Schottky measurements, and so once we take this MOS2 and MOSE2 heterostructure for photoelectrochemistry, the heterostructure which is having MOS2 on top is giving the better performance, and then we try to understand why this is giving the better performance. So it is giving the lower charge resistance and higher hydrogen generation. Then we try to understand using DFT. So of course it's an indirect band gap transfer, and when you do the projected density of states, it says that the valence band is totally dominated by the MOSE2, and the conduction band is totally dominated by the MOS2. That's a similar way which we got it from the XPS. And once you do the electron density transfer, electron density difference and localization function, it tells you that complete basal plane is activated once you have these heterostructures. And then we try to understand their band structure. So once MOS2 is on top, it shows the type second band alignment. That's what it is giving the better performance, and also your whole active basal plane is active. So that is the reason to have this high activity for these structures. Then after we try to understand the asymmetric 2D material, this has been first invented in 2017 by University of California, and because now the symmetry is broken, that's what they have a strong spin orbit coupling. So once they have a spin orbit coupling, their spin degeneracy is broken, so you have different states for up spin and down spin. So this is basically called the Raspa sprinting. So your some transition becomes forward, and under the magnetic field you can manipulate the spin now. So you can have a Raspa spinning in the valence band, and the conduction band you can have a G-man splitting. So once you use this kind of system like MOSSC, they don't have a magnetic element, but still due to the Raspa splitting, they behave a spin manipulation under the magnetic field. So we first have addressed the issue of the synthesis of MOSSC. So we filed a recently patent to synthesize MOSSC in facile way, Janus MOSSC, and then we do the photoelectrochemistry experiment. This is the band structures. It shows the Raspa type of splitting in MOSSC, and once you do the the splitting experiment as a cathode, you can see the 1.5 fold increment under the magnetic field. It's 0.4 Tesla, very less magnetic field. Then we try to understand what is happening, because MOSSC doesn't have any magnetic element, but still under the magnetic field it shows the increment. So it shows the lower charge resistance under the magnetic field, and also everything increases overall the performance. So we have done other part of physical property, magnetic measurements, MCD experiment. Though due to limited time I am not presenting here, but we try to understand the mechanism. So mechanism is like this: you have a Raspa splitting your valence band and G-man splitting in your conduction band. So what happens once you excite with the your photon goes, your electron from the valence band goes to the conduction band, as a hot electron, and it relaxes with a phonon. And phonon under this relaxation, under the magnetic field, is a spin dependent. So at the end, what you will have, you have a different probability of relaxation in this direction and this direction. So you get asymmetry in the relaxation. So that is where you have a asymmetry in spin electron density. So this diffuses. So it diffuses from a higher to lower density, and this is called the pure spin current. So this is where you have a spin current and the charge current, and this effect is called magnetogyrotropic photogalvanic effect. And due to this effect, you have a efficient charge separation, and the addition of the pure spin current give us this enhancement in this photocurrent, and also higher activity in the photoelectrochemistry. So this is the first proof of concept which you could able to establish, and I hope I could able to tell you that we could able to activate the Basal plane using the heterostructuring, and also the new area which we say that is a spin manipulated electrochemistry using the Janus 2D material has a lot more to do, and I am looking forward for the collaboration, not only for the fundamental but also for industrial research. And I of course acknowledge all my students who is working day and night for these experiments, and also all my funding agencies and collaborators. With that, I say thank you very much.
Thank you, Praveen. Our next speaker is Valentin Aleksandrovich from National Research Center, Kurchatov Institute of Russia. If you could raise your hand, the camera will find you. The talk is titled as Synthesis of Crystal Fluoride Superionics with Tysonite and Fluoride Structures by HTS Method.
Good day, colleagues. Let's begin. Allow me to introduce myself. My name is Valentin. I'm here today on behalf of the National Research Center Kurchatov Institute. I'm the supervisor of the Laboratory of Experimental Modeling and Synthesis of Refractory Materials. My aim today is to discuss the prospect synthesis of crystal fluoride superionics with Tysonite and Fluoride structure by HDS method. It's now the modern type of batteries such as lithium polymer, lithium ion, and etc. In the case of specific power indicators have reached certain limit. Thus, promising batteries should have a high specific electrical energy, lower 3,500 watt-hour per kilogram, and theoretical volumetric energy density of more than 3,000-4,000 watt-hour per liter. This regard is increasingly difficult for this type of batteries to meet the needs. A further increase in the energy intensity of batteries is very problematic and comes down mainly to increase in the size of the batteries used and their number. At present, the main interest is in solid-state chemical current sources based on superionic conductors. Among these conductors, crystalline substances with a structural disorder of the lattice, which contributes to the high conductivity of fluoride ion in the solid phase, deserve a special attention. In the fluoride-based batteries, fluoride ion batteries (PIBS), the chemical reaction used to generate electricity is a solid-state reaction of metal with a fluoride ion. These superionic conductors have a number of significant advantages over lithium-ion conductors. Since fluoride-ion batteries are fairly new technology, they are quite expensive to manufacture. Which one of their main drawbacks? As of 2008, the theoretical cost of smartphone-sized solid-state battery is around $15,000. An electric vehicle battery will cost more $100,000. Now, in many ways, this fact is associated with imperfect technology for the synthesis of multi-component large-size fluoride single crystals. This paper presents promising, well-known crystalline materials with a fluoride ion conductivity based on lanthanum barium fluoride, cerium strontium fluoride, and calcium lanthanum fluoride solid solution crystals synthesized by horizontally direction crystallization. What is the HDSM method? The essence of the method is follows. A crystallized substance in the form of powder, crystalline solid, or ceramics is placed in the bottom shaped container, is depicted there. Is melted by moving the container through the heating zone, is there, and after that crystallize in the cooling zone, is there. To obtain a strictly oriented single crystal, its seed is placed in the top of the bottom there and visually observed both for the moment of seeding and for the shape of crystallization from. You know, the main difficulty of this method is creation of the thermal unit. The thermal unit should provide a high gradient region in the crystal growth zone and necessarily low gradient temperature region in the crystal cooling zone. This condition is very important for obtaining optically perfect fluoride single crystals. In order to fulfill this condition, CPU coal graphite thermal unit was proposed and developed in several modifications. Is depicted in the slide. In the slide 5 is there. It's kind of the blueprint of our thermal unit, and it's depicted the second part modification. The thermal unit is there. Now the design of the developed CPU and its modification is characterized by extreme processability. Thus, the basic CPU and its modifications consist of separate carbon graphite heat exalting modules and blocks. For example, there, and for example, the central block is consist of other part of modules. For example, these modules. Blocks are easily assembled with each other according to the Lego principle. This combination forms an integral design of CPU in the form of common heat exalting volume is there. And this volume makes it possible to reduce the total cost of crystallization process by growing crystals without additional energy. Additional equipment was also developed, and auxiliary dry briquetting apparatus (DBA) is depicted there with a CPU for obtaining solid anhydrous case, and a high temperature vacuum furnace is depicted there. The CPU for studying color center was developed. In the seventh slide showed a list of thermophysical parameters of the main materials used in the design of the graphite thermal unit. For example, we can see this as a kind of carbon, such as sigma flex, sigma bond, and etc. In the eighth slide, showed graphical dependence of the thermal distribution of the solid body of the other kind of unit. The picture number 1, the distribution of the CPU, the first modification, and the figure number 2 shows the distribution temperature of the CPU, the second modification. 9th slide showed as a kind of solid anhydrous case there. Now, and using this method, we were able to synthesize simple fluoride with the order of fluoride structures such as calcium fluoride, barium fluoride, strontium fluoride, as a compound like as a single crystal metal rare earths such as calcium fluoride, doped europium, cerium, thulium, and etc. You can look at their using HDSM method, we have achieved a high yield of substance large-sided single crystal up to 18%, which significantly reduces the cost of the technology. Thus, we synthesized a series of large-sized single crystal of fluorides, lanthanum, barium fluoride, solid solution crystals, cerium, strontium fluoride, solid solution crystals, and calcium, lanthanum fluoride, solid solution crystals. With different contents of the second component, these synthesized large single crystals of fluorides are crystalline matrices with their own fluoride on conductivity. These non-stoichiometric phases of heterovalence solid solution based on lanthanum, calcium, and cerium fluoride are optimal from the point of view of their application as materials of fluoride ion conductivity for creating solid-state electrolytes. The crystal lattice of these conductors is characterized by the high intrinsic anion disorder and upon intercalation of nickel fluoride of low valence. In the next slide, it's our lab team. And thank you for your attention.
Thank you so much, Valentin. Our next speaker is joining us online, Zheng from the Key Laboratory of Clean Energy Utilization, China. Sir, I kindly request you to turn on your video for the talk. The title of the talk is Electrostatic Absorption at Nano-Confined Space for High-Performance Supercapacitor Energy Storage. Sir, if you could raise your hand, maybe we could help you turn on the video privilege.
It's my great honor to attend this conference and give this presentation. I'm Bozen from Zhejiang University. My work is on the electrostatic adsorption at nano-confined spaces for high-performance and supercapacitor energy storage. First, I would like to give a basic introduction of the supercapacitors. The high-power energy storage technology can be used for efficient energy recovery, regeneration, and supply in many practical applications. Here I give a typical example of the energy recovery regeneration at the port. During the up and down of the load in rubbery tied gantry grains, the hoisting load is around 40 tons and the maximum hoisting height is 18 meters, and the power and the energy we can recover from this process around 2 kilowatt hours. And if we want to capture such an energy, we should use the energy storage devices that can provide the power of around 300 kilowatts. So the lithium-ion batteries is not suitable for such an application since due to the limited power density. As a representative of the high performance high power energy storage technology, supercapacitors can be used in such applications. So in contrast to the complex or redox reaction mechanism in batteries, the energy storage of the supercapacitor is basically relies on the ion adsorption and desorption at the electrolyte and the electrode interface. Professor Yuri Gogos and Patrick Simon have they published a paper on Science before about the supercapacitor and the battery energy storage. They compared the performance and discussed the possibility of replacing the batteries with the supercapacitors in practical power needed area. So from recent publications on Science and Nature papers, we can see that the supercapacitors and the related microscopy electrostatic adsorption mechanism are indeed hot topics. So from this point of view, the reviewing the electrostatic adsorption mechanism is very important since it can provide guidance for the design and fabrication of the electrode. So in our group, we conducted a lot of work on the multi-scale numerical simulation and microscopy measurements to review the atomic electrostatic adsorption mechanism. Convention the model fails to describe the confined nanometer pores on the electrostatic adsorption. So we use the MD simulation work to review the EDL structure in nanometer pores, and it shows obvious the size effect. As you can see from the figure, there are a lot of the unique ion structures in the nanopores. We also conducted experimental work to control the pore size of the two-dimensional graphene film, and it confirmed the size effect very well. And also another important nanoscale effect is called the edge effect. We found that the charge predominantly accumulates on the edge region, and the edge can provide a unique high power and energy density at the edge area. In this work, we also provide the inference of the solvent on the energy storage performance. We found the optimum solvent for the electrolyte to deliver the high power and high energy density supercapacitors. We also calculated the ion self-diffusion coefficient in the nano-confined spaces, since it's very important to determine the electrolysis, the conductivity, and also the performance in supercapacitor applications. We use the EQCM. It is a microscopy measurements technology to determine the mode in the nano-confined spaces. Basically, it has three modes: the ion exchange, ion adsorption, and ion desorption. So we found that the ionic dominated energy storage mechanism in two-dimensional nanometer pores. This is the experimental work results, and it can be used to determine the optimum pore size to deliver the high power density. Also, we use the NMR technology to quantify the ion population within the nanochannels during the charging process. We use the multi-scale simulation and the calculation works to determine the entropy and the thermal effects in the supercapacitors. We also discussed the possibility of using the constant charge and constant potential method to calculate the ion distribution and the ion transport in the nanopores. Based on this work, we try to achieve some high power and high energy density supercapacitors. Here we use the vertical graphene to conduct the active material and the current collector. Then we can get the quite a low electron transfer resistance and receive the ultra high rate capability and power density. This is the work that we combine the traditional EDLC and the pseudocapacitors to achieve both high power and high energy density supercapacitors. This paper we reported the ultra low working temperature supercapacitors. We use the wholly graphene electrode and mix the solvent organic electrolyte to expand the working temperature window of the supercapacitors. Finally is the conclusion and the perspectives. Now we can use the advanced plasma technology to achieve the scalable fabrication of the vertical graphene that can be used for the high-performance supercapacitors. And we publish a review, several reviews to discuss the possibility of using the advanced nanomaterials for the supercapacitor, high-performance supercapacitors. We also summarize the molecular dynamic simulations on the design of supercapacitor electrodes. Okay, that is my presentation. Thanks.
Thank you, Zheng. Our next speaker is Gurbunov Viktorovich, who is also joining us online.
Good afternoon.
They are from the Russian Academy of Sciences, Russia. And the talk is titled as Palladium Alloy-Based Membranes for Deep Hydrogen Purification and Separation of Gas Mixture.
Dear colleagues, let us to represent to your attention our presentation, Palladium alloy-based membranes for deep hydrogen purification and separation of gas mixtures. There are four main technologies for the purification of hydrogen and its separation from gas mixtures in the world. There are the purification with polymer membranes, cryogenic purification, pressure swing adsorption, purification with palladium alloy-based membranes. The single technology, which is both more cost-effective and most productive, is the separation of hydrogen by its selective diffusion through metallic membranes made from special palladium-based alloys. This is the hydrogen membrane technology that makes it possible to produce high-purity hydrogen. The volume hydrogen content is more than 6/9. This separation method is single stage, simple, reliable in operation, sustainable, and does not call for a preliminary hydrogen purification. The principal requirement for the membrane palladium-based alloys include the high hydrogen permeability, low dilatation capacity while saturating with hydrogen, stability in corrosive gas media, high plasticity and strength during operation in temperature range of 300–600 Celsius. The reliability and effectiveness of the membrane operation in various gas media also are related to the catalytic activity of a membrane alloy in a given medium and dynamics of hydrogen permeability and mechanical properties which are caused by structural and surface change occurred during operation of a membrane. A technology for the manufacturing of vacuum-type palladium alloy foils to 30 microns in thickness. You can see the schematic diagrams of the preparation of such foils. It should be noted that the melting of an ingot is realized in a pure inert gas atmosphere in using an electric arc furnace, a non-consumable tangents electrode, and water-cooled copper bottom. The rolling of ingots was realized with intermediate annealing in a vacuum furnace using 4 and 20 roll mills. This graph demonstrates one of the principal membrane characteristics, namely the specific hydrogen permeability of a number of membrane palladium alloys with yttrium, lead, copper, ruthenium, and indium with ruthenium. The structure of the alloys corresponds to the palladium-based solid solution. You can see the image of the structure of filtering membrane element. Filtering element consists of two palladium membranes, profiled steel frames, porous separation element, and nipple for gas output. This structure exhibits a number of advantages over the analogous filtering elements, whereas the 1. High performance, 2. Low palladium consumption, 3. Compactness. It should be noted that at present there are no high-performance installation equipment with palladium alloy-based membranes in the world. Laboratory low-performance installations are available. From the right, you can see photo of operating prototype of a plant with a maximum performance of 30 cubic meters per hour. The construction of plain filtering elements, which include palladium alloy disc, foil membranes 50, 100, and 150 millimeters in a diameter, and 30 and 50 microns in thickness, have been developed in the Baikov Institute of Metallurgy and Material Sciences, Russian Academy of Sciences, and pilot samples of chemical membrane elements have been fabricated. In accordance with the volume and purity of recurrent hydrogen currents, the metallic filtering elements are considered as an alternative to pressure swing adsorption installations. The pressure swing adsorption method can be used to prepare hydrogen no more than 99 points and 995%. Such an installation has a fairly high cost. The multi-stage process for the hydrogen separation does not allow the method to be used in autonomic and mobile-powered installations. To increase the performance of filtering elements, the hydrogen flow is inversely related to the membrane thickness, and to save palladium, it is necessary to decrease the membrane thickness. A composite membrane, which a function layer for microns in thickness, was designed in the Baikov Institute of Metallurgy and Material Sciences, Russian Academy of Sciences. The porous titanium oxide was used as the substrate. The function layer was deposited by magnetron sputtering. Figure shows an image of a portion of the transverse section of the composite membrane. The performance of the membrane for a heating cooling cycle and specific hydrogen permeability, which is given in comparison with that of the membrane manufactured from the palladium plumbum. The values of the hydrogen permeability of the membranes differing in the configuration are comparable. This indicates the fact that the hydrogen flow is inversely related to the membrane thickness, and the porous substrate does not affect the permeability of membranes.
Thank you, Semyon Viktorovich. Our last speaker for this day is Yu Chao, professor from the School of Cyber Science and Engineering, Wuhan University, China. They're joining us online and presenting a talk on spatial-temporal domain charging optimization and charging scenario iteration for EV.
Good afternoon. This is Professor Yue Chao from School of Cyber Science and Engineering, Wuhan University in China. Today, the title of my presentation is Spatial-temporal domain charging optimization and charging scenario iteration for electric vehicle. Nowadays, due to the influence of environmental pollution and CO2 emission on Earth, the Committee on Climate estimates the battery EV will compromise up to 37% of the current van fleet by 2030. Meanwhile, the China government would also promote high-quality development for EV industry by 2035. Our UK government has committed to achieve net zero emission by 2050. This is a general framework of the EV charging system. So firstly, the charge station and the electric vehicle are a pair of service client and operator. The charge station will normally maintain the information such as energy storage, energy price, remaining charging time, and number of EV being parked, while the EV as a client will provide the traveling path, park duration, arrival time, and even the estimated charging time. With this, we can further facilitate the emergent ICT technology such as cellular network communication, vehicle-to-infrastructure communication, and vehicle-to-vehicle communication as an enabler to trigger the information exchange within the charging system. And lastly, we turn to the charging recommendation and charging scheduling, which are under the umbrella of service optimization. Additionally, we can also utilize the renewable energy to refuel the charging system. In summary, the EV charging system is quite interdisciplinary, covering the information communication technology, transportation planning, energy management, and vehicle control. Next, we will introduce our research work and the three types of service modes. Firstly, the plug-in charging mode is quite emergent and now being widely used in the world. It's normally with high charging power being supplied by the fixed charging port. However, it may suffer from high charging congestion and high grid loads, mainly due to the massive number of EV being charged simultaneously. The battery swapping mode, in contrast, can provide a quite low service waiting time by replacing the battery of the EV. However, it may suffer from a high operation and deployment cost, mainly in terms of charging battery station. The vehicle-to-vehicle charging mode is quite flexible by enabling an EV as an energy supplier to transfer energy to others with charging demand. This work can alleviate the dependence on charging infrastructure, can also trigger the service and any flexible charging points or parking lots. However, it's mainly work under low charging power. Next, we decouple the EV charging system into when-to charge and where-to charge, which are quite easy to understand. So on the left-hand side figure, it shows when to charge in time dimension, while the right-hand side figure just shows where to charge. We aim to coordinate the spatial and time dimension optimization as a holistic way. The first we are going to introduce is temporary spatial optimization and UFC policy. Here, the UFC policy stands for which EV is with the priority to preempt charging at the charge station. This work introduced the UFC-based scheduling policy to allow EV with high charging urgency get the preemptive charging. Meanwhile, we introduced the reservation service to predict the charge station availability and thus to able to allocate EV charging in advance. This work is with challenges such as how to provide the flexible charging based on prioritized user requirements. Meanwhile, how to optimize EV charging and the temporary and spatial dimension. We implement our scheme and the Helsinki city in Finland with several literature work for comparison. The objective is to maximize the total number of EV being fully charged. Meanwhile, to minimize the trip duration for all EV. According to the results, we're able to show that most of EV are able to be charged fully within their limited parking duration and our scheme. Next, we try to integrate the plug-in charging and the battery swap system. So this work aims to switch the optimization service and the two modes according to passenger service requirements. Meanwhile, to provide a dual queuing optimization system to establish a stable and hybrid charging framework. This work is with challenges such as how to take advantage of the two modes to satisfy the user demand. Meanwhile, how to maintain the load balance between the grid and the charging infrastructure. According to the results, we're able to show that with this, most of you are able to refuel the energy timely, meanwhile, to meet the travel demand. So this work is with potential for the public transport service, such as the public electrical taxi. Lastly, we introduced the work for vehicle-to-vehicle charging, which includes the vehicle-vehicle pair matching and parking lot selection. So the left-hand side figure just shows whom to pair for charging, while the right-hand figure just shows where to implement charging. So this work aims to obtain the vehicle-to-vehicle charging requirement of EV and match them in a pair. Meanwhile, to combine the multiple queue optimization to recommend a suitable parking lots. Normally, there are three network entities in this scenario, which are the end consumer, end provider, and the parking lot. The objective is to maximize the charging quality of the experience for pair of EV. Meanwhile, to minimize the average charging waiting time at each parking lot. According to results, where suffer from challenges such as the uneven charging requirement between pair of EV, and also the unsuitable vehicle charging lot selection. So with our system for optimization, we are able to show that the vehicle charging mode is able to alleviate the burden on charging infrastructure, but in future, it may be complementary to the plug-in charging or even the battery swap system. So lastly, we turn to our simulation platform, which is developed based on an open source platform, namely the opportunistic network environment. We have implemented the full stack EV charge system on top of that, and now can support several features, such as to import Google Map, and meanwhile to run the load analysis of charge station. Rather, our publications and award. So in future, we aim to integrate the autonomous vehicle, cybersecurity, hybrid energy supply, and even air-ground cooperation to achieve the sustainability of the e-mobility ecosystem. So if you have any questions, just send me an email. Thank you very much.
Thank you, Yuchao. Now we have the question and answer session.
The online participants, please type in the questions in the chat box and our AV team will relay to us. For the offline participants, please raise your hand and you can also use table mics for asking the question.
Thank you. I have a question to both of speakers, this Gurbunov, Semen, and Valentin. I can't spell their surname, sorry. As in area of petroleum geology, we have some type of analysis, we call it artificial maturation. During this analysis, we are performing welding of gold and platinum cells. Can you show, please, your expertise or give any recommendations how to improve hermetic properties of these materials after the process of gold or hold welding of gold and the platinum cells? If it's in your area of interest.
Thanks for the question, and we have several processes, and like as artificial materials such as crystalline or ceramics, we have a process of annealing. It's a big process of annealing, and speaking friendly, my presentation was devoted by this thermal unit, and this thermal unit propose to grow on crystal without additional annealing, and we can cut off this process on the half of this, and it's the first additional improving of this crystal. And the second, we're using radiation, and we have a very powerful sources on our institute, and we radiate our crystal, and some how to say, and the determine quantity of radiation enhance of fluoride ion conductivity of this material. Thanks.
Thank you. Next question.
I have the question for the first report, Nikhil Kumar. I'm so sorry for the pronunciation of the names. And from your report, we can know that the synthesis for the lanthanum consisting material can be this material can synthesize only after 1030 degree. And is it only after this temperature lanthanum can occupy the positions in the crystal structure of the material? Or have you ever tried to cut on this temperature? And if yes, what products have you obtained in these cases?
Actually, after this temperature, we have not tried, but at this particular temperature, we got two mixture of phases. The other phases was lanthanum oxide, which was very less, but it was present in that CLSR material. But beyond 1300, we have not tried that.
And another question, will be it interesting for you to use and to compare the different materials, maybe from our laboratory, which we can synthesize at more little temperature, and with materials which have a crystal structure, and the crystal structure is very similar for your materials, and we can change the cations in the framework on the lanthanum too. Maybe if it will be interesting for you.
Yeah, of course. Welcome all things. I will receive. Thank you.
Okay, thank you.
If we can ask second speaker Gurbunov Semen if he has any recommendations and opinion about my question, if it's in area of your interest and if you're online.
Please repeat question. Gurbunov Semen.
Yes, I can repeat the question. In area of petroleum geology, we have analysis of artificial maturation. During this process, we are performing welding of gold and platinum cells. And my question is, can you show expertise or give any recommendation how to improve hermetical properties of those material after cold or gold or hot welding of golden and platinum cells? Or it's more, your area of interest more about palladium? Just palladium, probably.
Yes, we use gold cold welding for our membranes.
So you don't have the purpose of completing all those stages of hermetic at this moment. I mean, while you're performing welding, it's not in your task, right?
We use nickel suballoys between different materials.
Okay, thank you. Thank you. Any other questions?
Thank you. I have the question for the Zheng. Sorry for the pronunciation. What the predictable weight of such batteries, and is it really possible to use it for the planes industry without the loss of the limited for the symmetry weight? What do you think about it?
Zheng, if you're online. Unfortunately, he's not online. I'm really sorry.
It's okay.
Any other questions?
One else question for the last report. Yu Chao, yes. Could you tell why do you use the model of the processes only for Helsinki? Or in another works, you analyze another cities too, and maybe I lost this information, maybe.
Right. Sorry. So first, I'm alive, and the second, my first suggestion. The reason I am unsure here is a virtual city mode that we have been used for several years. But you're right. In addition to this Helsinki city I do have the map for one of the country in India, the Nidavi, and also we have several maps from major cities in China, such as Zhejiang, who is now popular for using electrical taxi for running their business modes. But in addition to this one, I also have several maps being able to use for to show the scalability of the scheme.
Thank you.
Thank you. Now, sorry, one more. So depending on the development of the city, I think there's also the impact of deployment of charging infrastructure onto the performance of masking. But there's another story. My side is how to schedule those EV charging based on what we already deployed in the city, rather than where we deploy in advance and then trigger the EV to charge.
Thank you.
Thank
Thank
you.
you.
Any other questions we could take? Online participants, if you have any questions, you can.
Thank you. For the first, Nikhil Kumar, I have a little question about the size of the cell. Could you tell about the size of the cell? The size and the operation temperature.
Size is
Fuel
one.
cell, yes, the size. You have
Actually,
a polarization.
we have made button cells according to our palette maker.
On the slide, I see the polarization curves, yes?
Yes.
You registered it in the cell. Fuel cell, in the cell, in the device. What's the size of the device?
That is 14 mm
14.
dia size of that. It's according to that the palette maker size. So we have 14 mm, so we have made the size of 14
And
mm.
what temperature? What temperature of the process?
For testing? For testing temperature or just synthesizing?
No synthesizing. You show the polarization curve,
Yeah,
yes?
it's from 600 to 400. 600 to 400. 600, 550, 500, 450, and then 400.
Okay, thank you.
Any more questions? Online participants, if you have any questions, you can type in the chat.
I have the question for the third report, Praveen Kumar. And how do you think other claim like materials, maybe the nature minerals like a montmineralite, which have a very similar crystal structure and layers and 2D structure, can these materials be used in similar processes or not?
Yes. Actually, these 2D materials, when you exfoliate, they have a very high surface area. You can utilize complete basal plane. So if you can exfoliate any of the material in that 2D forms, you can utilize the property of those 2D materials. So only the material which has a van der Waal in the Z direction can be exfoliated. Not all material you can exfoliate in 2D forms. So that is where these 2D materials are gaining a huge interest for advanced application, not only for electrolysis, but other optoelectronic applications also. These 2D materials are going to be useful for next generation devices.
So we can use it. Yes?
Yeah, we can use it.
Thank you.
Thank you. There is a comment from Gurbunov online. He says, we have a patent for diffusion cold welding of platinum membranes and use nickel intermediate layer. Gurbunov, just for clarification, is it a question? I think he was answering one of the previous questions which was asked.
Now we have come to the end of our session. We'll have more interesting speakers tomorrow from the same session of sustainable energy and energy storage. Right now, we have arranged a treat for you, which is a musical performance from the JNCSR research students. While we wait for them to assemble, I would like to thank the chairs who are chairing the session, Dr. H.S.S. Ramakrishna Mate and Dr. Bhagavatullah L.V. Prasad, who was kind enough to accept our invitation. Thank you so much. We would also like to thank all the speakers from the session of sustainable energy and energy storage, both online and offline. We would also like to thank the audiovisual team, Ms. Aarti, Ms. Anushka, and Ms. Mallika. Give them a hand of applause, please. Let's also thank Rituprova Sen and Rahul Dubey, who are very actively behind organizing all the talks and the videos in order all throughout the day. Finally, let's thank Kamakshi and Kuku, who are helping you with the mics. Let's also thank the chairs, myself and Akshaya.
The cultural evening for tonight will start at 5:30. So we will have a tiny break till then. You can walk around and explore till then and come back soon. Thank you.
नहीं ये किसका होना ये किसका होना और तो ये
कीबोर्ड आपका उससे कनेक्ट नहीं होगा तो फिर दो
एक माइक और चाहिए था उतना भी स्लो नहीं हाँ बिल्कुल अरे आ गए भैया भैया आ गए इनका माइक का वो बढ़ा दो माइक का साउंड बढ़ा दो सुबह साउंड नहीं आ रहा था हाँ
भैया
अभी आ रहे क्या बताएंगे अब कैसे बताएंगे हाँ मोरल सपोर्ट देना है हाँ हाउ स्वीट रहने दो
प्रोफेसर हो रहा है
हम बैठेंगे
ये क्या कवर निकाल अच्छा वही है एक मिनट
बढ़ा दो बढ़ा दो नहीं था हाँ हाँ मैंने देखा
बैठ रहा हूँ
एक माइक कम है लेकिन क्योंकि अभी ये चार ही लगेगा
पीछे का
हेलो हेलो
हेलो हेलो
हेलो
अच्छा साउंड है ना ध्यान से
मैं उधर बैठ रही हूँ
नहीं
हमको दो नहीं चाहिए
Color mic, I don't need anything. It's fine. मेरा color mic है.
एक ले लो आप लोग इंडिविजुअली गाओ हम दोनों इसमें शेयर कर लेंगे
मैं इंडिविजुअली गाऊंगा. You need one. एक यहाँ पर
ठीक है ना मैं भी इसे शेयर कर सकता हूँ ना
अरे एक और भैया भी तो आ गए
पर भैया को गाना ही नहीं आता
उधर दो है ना, तो इधर एक लिया। अरे नहीं, काफी है।
हाँ आप उधर चले जाओ।
स्पीकर में नहीं हो रहा है। मैं इसी पे सुना ही दे रहा है। इधर
उधर मत लेना, मुझे बहुत जगह पकड़ना है।
हेलो हेलो हेलो।
हेलो हेलो
हेलो हेलो।
कुछ कुछ नहीं है, माइक ले लो।
भैया को बीच में करते, गर्ल्स बॉयज
ठीक है।
एरोप्लेन में
अच्छा एक बार माइक देख रहे थे। यस पूरा शिफ्ट हो जाओ।
ठीक है।
हाँ गर्ल्स बॉयज इधर आ जाओ। थोड़ा और उधर
ये मूव करना पड़ेगा, ये मूव करना पड़ेगा मुझे।
ये सेंटर पे होना चाहिए। नहीं और नहीं हो पाएगा।
अच्छा ये थोड़ा मूव हो गया थोड़ा। हेलो हेलो हेलो। राधे भाई थोड़ी बहुत तो आवाज नहीं आ रहा। दिन ताना नहीं आ रहा, नहीं आ रहा।
कागज के दो पंख लेके दोनों शेर नहीं हो पा रहे। माइक दे दो आप, फिर सब गा देंगे। दोनों का नहीं हो रहा है। ये बहुत बहुत धीरे आ रहा है। अगर मैं सामने लाऊंगी तो मैं गा पाऊंगी।
एक मिनट क्या हुआ क्या हुआ। 10 इसको बोलिए बहुत ज्यादा
कैसे लग रहा है
इंक्रीज। दिन ताना आ रहा है
पर बहुत दूर से मेरा ऐसे आवाज बहुत धीरे है, नहीं आएगा।
तुम एक काम करो दिन, तुम्हारे थोड़ा प्लीज तुम थोड़ा जोर से गाओ। तेजस्वी थोड़ा तुम्हारे तरफ थोड़ा कम
तुम मेरे थोड़ा पास है। ठीक है
तुम इधर बैठना, आधी कुर्सी पे छोड़ के। दिन ताना
कुछ और गाने गाओ, इनको कंफ्यूज कर।
आई एम प्रैक्टिस
23 मिनट
1500 ये दीदी को बोलो, दीदी दीदी दीदी
मुकम्मल कर दिया वो जो याद बाकी है, वो जो याद बाकी है, इश्क है प्यार हाथ लगाऊं दिल बीते सारा
अरे वो नहीं
वो सुन ले
बिखरने बिखरने
और कॉलर माइक नहीं है क्या?
Yes.
और कॉलर कर प्लीज करने का मुझको
शौक है बड़ा तेरा मुझको, तू बता जरा दिखने का मुझको शौक है बड़ा तेरा मुझको, तू बता जरा
डूबती है तुझ में आके मेरी कश्ती गुफ्तगू में जो बहुत तुरंत कर लेता है। हम दोनों में प्रॉब्लम होगी, तेरे को इधर आना पड़ेगा।
तुझे इधर आना।
हाँ नहीं हो पाया।
रीजनल टच
राजस्थानी गुजरात साउथ तक कोई नहीं रख पाया।
वो तो
राज निकल गए।
मैं ना कभी कभी माइक ले लूंगी।
लेकिन वो
हेलो पानी
Welcome back, everyone. We present to you the Jain CSR Cultural Committee team, which is a wonderful fusion of research students who nurtures the music, dance, and arts from all regions of India with great diversity. Today, they showcase the language of music, which doesn't have barriers. Let's welcome them with a big applause.
welcome everyone to our cultural committee. So this program, short program. So we will be presenting a short medley to all of you. Hope you all will enjoy.
कागज के दो पंख लेके उड़ा चला जाए रे, जहाँ नहीं जाना था ये वहीं चला आए रे। उम्र का ये ताना बाना समझ न पाए रे, जुबां पे जो मोह हमारा लगाए रे, जाने न दाए रे। दिशा हरा केमन बोका मुंटा रे। कागज के दो पंख लेके उड़ा चला जाए रे, जहाँ नहीं जाना था ये वही चला आए रे। उम्र का ये ताना बाना समझ न पाए रे, जुबां पे जो मोह हमारा नमक लगाए रे, कि देखे न भाले न जाने न दाए रे। दिशा हरा के मन बोका मुंटा रे। ये सारी कोयले बनी है आज डाकिया, कुहू कुहू में चिट्ठियां पढ़े मजाकिया। ये सारी कोयले बनी है आज डाकिया, कुहू कुहू में चिट्ठियां पढ़े मजाकिया। इन्हें कहो कि ना छुपाए किसमें है क्या बताए, उसकी आज मैं नजर उतार लूं, सवार लूं है सवार लूं, सवार लूं है सवार लूं। हवा के झोंके आज मौसम से रूठ गए, गुलों की शोखे आज भंवरे आके लूट गए। बदल रही है आज जिंदगी की चल जरा, किसी बहाने क्यों न मैं भी दिल का हाल जरा सवार लूं है सवार लूं, सवार लूं है सवार लूं। मैं कोई ऐसा गीत गाऊं कि आरज़ू जगाऊं, अगर तुम कहो। मैं कोई ऐसा गीत गाऊं कि आरज़ू जगाऊं, अगर तुम कहो। तुमको बुलाऊं या के बिछाऊं, कदम तुम जहाँ जहाँ रखो। ज़मीं को आसमां बनाओ, सितारों से सजाओ, अगर तुम कहो। मैं कोई ऐसा गीत गाऊं कि आरज़ू जगाऊं, अगर तुम कहो। नवराई माझी लाडाची लाडाची ग आवड हेल चंद्राची चंद्राची ग नवराई माझी नवसाची नवसाची ग अप्सरा जाशी इंद्राची इंद्राची ग चली शर्माती घबराती वो पिया के घर ठिलाती बल खाती वो सुरमई नैना छलकाती छलकाती वो पिया के घर भरमाती सकुचाती वो सुनियो जी इसको रखियो जतन से मुरली नाजुक है नाजुक है नाजुक कली है अनमोल कली है अनमोल आओ जी आओ ठुमका लगाओ जरा बहको जी बहको खुशियों के बाजे ढोल खुशियों के बाजे ढोल नवराई माझी लाडाची ग आवडा हेला चंद्राची चंद्राची ग नवराई माझी नवसाची नवसाची ग अप्सरा जाशी इंद्राची इंद्राची ग छुप ना जाओ जी दीद कराओ जी क्यों तरसावे हो मन सकल दिखाओ जी थारी सब जानू मैं चौधरी मन से जी मैं कह लगी मरे हिबड़ा में जागी ठोकड़ी रे चंदा में थारी चांदनी मन दामन में बांधी खुशी रे झूम 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 मरे हिबड़ा में जागी ठोकड़ी रे चंदा में थारी चांदनी मन दामन में बांधी खुशी रे झूम 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 ओ लोग छुप ना जाओ जी दीद कराओ जी क्यों तरसावे हो मन सकल दिखाओ जी थारी सब जानू मैं चौधरी मन से बोल जी मैं कह लगी हरे हिबड़ में जागी ताकने रे चंदा में थारी चांदनी मन दामन में बांधी खुशी रे झूम 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 हरे हिबड़ में जागी ताकने रे चंदा में थारी चांदनी मन दामन में बांधी खुशी रे झूम 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 गुड़िया रे गुड़िया गुड्डा परदेसिया चोरी आसमानी हो गई शगुन पे देखो चांदमानी हो गई गुड़िया रे गुड़िया गुड्डा परदेसिया चोरी आसमानी हो गई शगुन पे देखो चांदमानी हो गई आजा तुझे को पुकारे तेरी परछाइया रे फकीरा कैसा तू है निर्मोही कैसा हर जाइया उड़ गए तो तेरे गए तो उड़ गए तो तेरे उड़ गए तो तेरे गए तो उड़ गए तो तेरे तेरी आंखों से हुई यारियां चलते चलते हुई मेरी आंखों ने तेरी आंखों से अब बीती गई तेरी आंखों के बीच बीच हम पगले से चल पड़े चक्कर में कुछ भी ना सुनती है, दिल ये धोखाधड़ी कर देगा, सोचा न था इतनी ये गड़बड़ी कर देगा, सोचा न था ऐसी मुश्किल कड़ी कर देगा, सोचा न था। उड़ गए तो तेरे उड़ गए तो तेरे उड़ गए तो तेरे उड़ गए तो तेरे। गरे गरे सा 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 रे गा, गरे गरे सा 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 पा धा सा मा 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 प रे गा गरे गरे सा नि सा धा नि सा, गरे गरे सा 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 रे गा, गरे गरे सा 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 रे गा। बेरंग सी है बड़ी जिंदगी, कुछ रंग तो भरो, मैं अपनी तन्हाई के वास्ते अब कुछ तो करूं। जब मिले थोड़ी फुर्सत, जब मिले थोड़ी फुर्सत, खुद से कर ले मोहब्बत, है तुझे भी इजाजत, कर ले तू भी मोहब्बत, है तेरा दिल मेरा मुझसे कह रहा, तू ख्वाब सजा, तू जी ले जरा, है तुझे भी इजाजत, कर ले तू भी मोहब्बत, है तुझे भी इजाजत, कर ले तू भी मोहब्बत। जीवन डगर में, जीवन डगर में, जीवन डगर में, प्रेम डगर में, आए नजर में जब से कोई है, तू सोचता है, तू पूछता है, जिसकी कमी थी क्या है वही है, हाँ ये वही है, हाँ ये वही है। तू एक प्यासा और ये नदी है, काहे नहीं इसको तू खुल के बताए, जो है कहे, जो है सुने, वो बात क्या है बता। कोई कैसे उन्हें ये समझाए, सजनिया के मन में अभी इनकार है, जाने बलमा घोड़े पे क्यों सवार है, जाने बलमा घोड़े पे क्यों सवार है। धीरे धीरे जतन करने से दुल्हनिया के खुलते हृदय के द्वार है, जाने बलमा घोड़े पे क्यों सवार है, जाने बलमा घोड़े पे क्यों सवार है।
निगाहों में देखो मेरी जो है बस गया, वो है
तुमसे जाने तेरी आँखें थी बातें थी वजह, हुई तुम जुने की आरज़ू, तुम पास होके भी, तुम पास होके भी, एहसास होके भी, अब ये नहीं ऐसे है, हमको गिले तुमसे न जाने क्यों मीलों के है फासले, तुमसे न जाने क्यों। कैसे बताए कि तुझको चाहे, जरा बता ना पाए। बातें दिलों की देखो जब आके आके तुझे समझाए। तू जाने ना, तू जाने ना, तू जाने ना, तू जाने ना। आओगे जब तुम ओ साजना, आओगे जब तुम ओ साजना, खिलेंगे बरसेगा सावन, बरसेगा सावन, झूम झूम के दो दिल ऐसे मिलेंगे। आओगे जब तुम ओ साजना, आओगे जब तुम ओ साजना। आया फूल खिलेंगे, नैना तेरे कजरारे हैं, नैनों पे हम दिल हारे हैं। अनजाने ही तेरे नैनों ने वादे किए कई सारे हैं। सांसों की मध्यम चले तुझसे कहे बरसेगा सावन, बरसेगा सावन, झूम झूम के दो दिल ऐसे मिलेंगे। आओगे जब तुम ओ साजना, फूल खिलेंगे, फूल खिलेंगे। किसी शायर की गजल जो दे रूह को सुकून के पल, कोई मुझको यूं मिला है जैसे बंजारे को घर। मौसम की सहर सर्द में दोपहर, कोई मुझको यूं मिला है जैसे बंजारे को घर, बंजारे को गुलाबी आंखें जो तेरी देखी तेरा भी ये दिल हो गया। संभालो मुझको ओ मेरे यारो, वरना मुश्किल हो गया। गुलाबी आंखें जो तेरी देखी, शराबी ये दिल हो गया। मैं लुट गया के दिल का कहा, मैं कहीं का न रहा, क्या कहूँ मैं दिलरुबा। पूरा ये जादू तेरी आंखों का, ये मेरा कातिल हो गया। गुलाबी आंखें जो तेरी देखी, शराबी ये दिल हो गया।
Thank you.
A big round of applause for our cultural committee. So this concludes our day, and I would also like to thank the AV team and the people who managed the stage for today. Mr. Srinath, Dilip Kumar, Mune Gowda, Mohammad Pir and Srinivas R. A big round of applause for being behind the stage and helping us control the event today. Thank you so much. Thank you, Cultural Committee. And we can now break for dinner. The dinner is arranged at Conference Dining Hall, and you can follow our volunteers for the same. Yeah, same place as lunch. And all the Indian speakers who have come, kindly bring the travel documents tomorrow for reimbursement purposes. We will be sitting there at the help desk and helping you with the same. Thank you, everyone, and see you all tomorrow. Thank you.